distributions and applications. So this is going to be a sort of follow-up to the talk I gave yesterday. So yesterday I defined real stable polynomials. And so today is sort of the probabilistic analog of these polynomials. We see that they have a lot of nice properties in probability theory. So just to remind you of what we talked about yesterday, we said that a polynomial P is real stable if it has no roots in the upper half complex plane. We talked about many closure properties of these real stable polynomials. For example, if you plug in a real number or a complex number with non-negative imaginary value, the resulting polynomial remains stable. If you do partial differentiation, it remains stable, and so on. Okay, so now, let me start talking about probability. So let's say mu is a probability distribution. So for most of the talk, I assume I have a set of n elements from 1 to n. I'm looking at subsets of this set. So mu is basically a distribution on subsets of the numbers from 1 to n. Now, there is an important definition called the generating polynomial of mu. So it's defined as follows. You write down the expected value of, let me you look at, let me call it G mu. So G mu is the generating polynomial of mu on variables z1 up to zn. It's equal to the expectation of z to the s. Okay, so let me rewrite it. So this is basically the summation of over all sets, which are subset of numbers from 1 to n, the probability of s under mu times z to the s. Okay. Again, to put it differently, this is just summation over all sets S, which are subset of 1 to n, mu of S times the product of zi for I in S. Okay, so this is called the generating polynomial of mu. Let me do an example. So let's say you have two Bernoulli random variables, b1 and b2. Let's say b1 has prior p1 and b2 has prior p2. Now I want to write down, so these are independent. I want to write down the generating polynomial of this distribution. So with probability p1 times p2, they both come up head. So I'm going to get z1, z2. Then with probability p1 times 1 minus p2, I get only the first one. With probability, so I can have z1. With probability p2 times 1 minus p1, I only have the second one, so I get z2. And then with probability 1 minus p1 times 1 minus p2, I have nothing. Okay, so that's a generating polynomial. You can rewrite this polynomial differently as follows. You can write it as it's really p1 times z1 plus 1 minus p1 times p2 times z2 plus 1 minus p2. Okay. Now you see each of these polynomials is real stable. And I have product of two real stable polynomials. So the generating polynomial of this independent Bernoulli random variables is a real stable polynomial. So this is I'll get to the definition of a strong Rayleigh distribution. So this is due to Borchia, Brendan, Liggett from 9. So many of the stuffs or statements about this, distributions come from this paper. So we say mu is a strong Rayleigh. Or let's shorten by SR if G of mu is real stable. Okay. So we already saw that two independent Bernoullis, or in fact, n independent Bernoulli give you a strong Rayleigh distributions. So I want to now give more examples, and then I'll talk about, closure properties and many other properties of these distributions. Any questions? No. So let's start. So next example 1, random spanning tree distributions.
Can you explain the choice of the name?
I'll get to that like in 20 minutes. Okay. So what's a spanning tree distribution? So let's say you have a graph G. I want to look at the uniform distribution over all the spanning trees of this graph. So the generating polynomial is just is basically let's say you have like m edges, e1 up to em. The generating polynomial is just summation over all spanning trees t, z to the t. Okay. Now I claim that for every graph G, this polynomial is a real stable polynomial. So the corresponding distribution is strong Rayleigh. Now how to prove it? It's again by like Cauchy-Binet, mother of all stable polynomials. So here is the proof. So let me say that the simple lemma that G mu is real stable for all G. The proof is that if I look at this polynomial, determinant of 1, 1 transpose over n plus summation over all edges E, ZE, L of E. What is L of E? L of E is the Laplacian of the edge E. So this is the matrix which is 1, 1 at the endpoints, like if edge E is UV, so it's 1, 1 at the UU and VV entry, and -1 at the UV and VU entry, and 0 everywhere else. So this is the Laplacian of the edge. So this matrix LE is a rank 1 matrix, it's PSD, so on. And this polynomial, again from this mother of all stable polynomial theorem, we know that this is a real stable polynomial. So this is real stable. And I claim that this is exactly the generating polynomial of all the spanning trees in the graph. Okay, if that is true, then this is a strong Rayleigh distribution. So how to prove that? Let's basically what you do is that you do the Cauchy-Binet, you use the Cauchy-Binet theorem again. So here I have rank 1 matrices. Remember, Cauchy-Binet says that when you have this, you're looking at determinant of sum of rank 1 matrices, you can write it as, you can choose every n of them, look at the determinant of that, and then sum it over. So I look at over all sets S of n of these rank 1 matrices and a determinant of that. There is one technical thing, which is that all of these Laplacian matrices are orthogonal to all ones. So if I choose my whole set S from here, I get 0. So I have to choose this 1, 1 transpose and n minus 1 of these guys. So that these only give me the non-negative, non-zero terms. So I'm going to have summation over all sets, let's say, T of size n minus 1 of edges. Determinant of, so always have to have 1, 1 transpose, so 1, 1 transpose over n plus summation of ZE, LE for E in T. Okay. Now, again, similar to what Nikhil has been doing a lot. So this is determinant is a linear function in the ZE, so you can factor out the ZEs. Basically, I can send this out. This is really Z to the T. So now the question is, what is this determinant? And that's something you can do. You can just calculate. So the thing is, these matrices are all orthogonal to the 1, 1 transpose. This gives you eigenvalue of 1. The Laplacian matrices of the edges, you can see basically so this would be equal to 0 if T is not a tree. Why? Because if T is not a tree, because it has n minus 1 edges, it must have a cycle. And you can see if you have a cycle, the summation of the Laplacian, like the Laplacian of the edges are linearly dependent, so you get a 0 determinant. And otherwise, you get 1. So otherwise. And okay, this is not all. I mean, we can do the calculation. It's not hard to see. Anyway, so what you're going to get is that this is exactly equal to this polynomial. Any questions? Okay. So this is example 2. Now I want to, or example, I guess 2, maybe the 1 was Bernoulli's. Now let's say example 3. So it's called determinantal point processes. So how are they defined? Let's say we have a PSD matrix. So given a PSD matrix, let's call it K, which is a n by n matrix. I want to define a distribution. So I choose a set S. The probability of a set S is proportional. Probability of S is proportional to the determinant of K of S comma S. So what is K of S comma S? Let me write it right here. So if this is K, this is S. So this is S, this is S, this is K of S comma S. It's simply the rows and columns, the submatrix you get by rows and columns indexed in S. Okay? So what's the determinantal point process? It says that like you have this kernel matrix, you look at every set S, you look at the corresponding submatrix, the probability of that is proportional to this to determinant of this. And the point is, because the matrix is PSD, these determinants are non-negative, so this is a well-defined probability distribution.
By proportional, you mean you just have to normalize to 1?
Yeah, there's a normalizing constant, which is summation of all of these things. Good. Now there are 2 questions I want to answer. First, you can ask, who cares? Like, why is this interesting? And the second one is that is to see that this is a strong Rayleigh as well. Okay, so let me first say, who cares?
In the definition, do you fix the size of S, or you let S over?
For now, it can be anything, but yeah, there is a. I'll talk about a special case where you fix the size of S later. Okay. So who cares? Okay, let me say there is an equivalent definition of this. If you have a PSD kernel K, you can write it as VV transpose, because it's to just do the Cholesky decomposition, where V is this matrix of V1 up to Vn. Okay, so the K is really the gram matrix of these vectors. Now, basically, pictorially, you can think about your vectors this way. Maybe this is V1, this is V2, this is V3, and so on. Now, what this determinant is that like the probability of 1 and 2 is really this thing. You look at this parallel pipe, you get by looking at V1 and V2, and you look at the volume squared of this parallel pipe. That's exactly that determinant I wrote there. So it's a volume squared of the parallel pipe that you get from V1 and V2, for example, is equal to determinant of the matrix, the gram matrix of a V1 and V2, the matrix which has entry V1, V2, like the 2 by 2 matrix, where the ij entry is just the dot products. And more generally, like if you have k vectors, the volume squared is exactly the determinant of this k by k matrix. You get k by k inner product matrix. Okay? Okay, so that's another way to look at it. Now, what does it say about who cares? So the thing is, now suppose you are in in some practical setting. These vectors represent some documents, like feature vectors of documents, web pages, and so on. And what you're interested in is that you want to choose a set of, let's say there is a web search, like a query web search for some query. You want to return relevant results, but you want to diversify the set of returned answers. And like one way to do that is to maximize the determinant. And the reason is that when you maximize the determinant, you try to choose a set of vectors that not only have large norms, but also they are have large angles with each other. Okay, so that's the point of looking at a determinant. So in practice, we use this to maximize diversity. Now there's a whole literature on this. There is a lot of people in machine learning are using this. There's a very beautiful survey by Kulesa and Taskar on applications and theory of these determinantal point processes. Now, one thing I want to say is that they are actually a special case of these strong Rayleigh distributions. So the simple lemma that DPPs are strong Rayleigh. So how do you prove that? Again, you use the mother of all stable polynomial theorem. So you basically write this thing. You write down determinant of I plus summation of Zi, Vi transpose. Okay, so again, this is a real stable polynomial because this is symmetric. These are rank 1 PSD matrices. When you open this up, again, you have to use Cauchy-Binet. This time it's a little bit more involved Cauchy-Binet, but basically, when you open this up, it turns out that now again you have to choose n vectors, but I haven't said how you decompose I. There are many ways to decompose I. The right way to think about it is that you choose any subset of these vectors, which are linearly independent, and sort of complete it by adding vectors from I, which are orthogonal to the vectors you've chosen so far. So this thing is exactly equal to summation over all sets S, subset of 1 to n, of determinant of, okay, so it's not really determinant, so let me say what it is. So it's Vi transpose. So this is determinant, so let's say all sets, okay. So it's determinant S. So what I mean by this notation, it means that you don't, so these vectors I have here, let's say I have k vectors here, and k is less than n, then the determinant of this is 0, but you don't compute the determinant. You actually, this object means that you compute the summation of the determinant of all principal minor, all k by k principal minors of this matrix. Okay, so that's exactly what Cauchy-Binet tell you. Another way to think about this object is that this is also equal to determinant of the Gram matrix of Vi Vj's for I and j in S. And you have to also multiply by root Zi, root Zj. So you can then factor out Zi's outside. So this is Z to the S. Okay. So there are two Cauchy-Binet going on here, but okay, I don't want to go in.
Just the elementary symmetric function, right? In the eigenvalues of the.
Yes, exactly. So this is the kth coefficient of the elementary of the characteristic polynomial of this matrix. Yeah, that's true. So you can actually compute these things just by looking at the characteristic polynomial of the matrix. Anyway, so the thing is, okay, so the thing is, if you do the right Cauchy-Binet, you exactly get this volume squared of the parallel piped times z to the s. So this polynomial is also a real stable polynomial, and that's exactly the generating polynomial of the determinantal point process. Yes?
Well, what you said, there is an n choose k that multiplies, if I understand correctly what you said.
No, you don't multiply n choose k. You look at all k by k minors, and you sum them up.
The number of times it appears in the sum depends on its sum, if I understood what you said.
But each time it will appear from different set of vectors. So if I fix k vectors and a minor It will appear only once.
The z to the s remembers the subset, right?
What's that?
I think the answer is the z to the s remembers the subset.
S remembers.
Monomial, right? So generating quite
The
a
z to the s.
Yes, different for
Yeah, z to the s, yes. Z to the s remembers the subset, yes. Don't get confused with the fact that I'm counting a minor multiple times, because I'm counting it with respect to different set of vectors. So if you look at a minor, it has contribution from all k tuples of the vectors. And each k tuple is being counted for its particular monomial z to the s. So it's true, I will count a minor n choose k times, but they correspond to different monomials of my polynomial. So that's not an issue.
I mean, another way is that the elementary symmetry function is just the product of the eigenvalues, right?
Yeah.
They're only k non-zero eigenvalues.
Yeah.
So then you just replace v transpose by v transpose v.
Yeah. So there. Yeah. Okay. Good. So now we saw so far 3 examples of this strong line distribution: independent Bernoullis, random spanning trees, and DPPs. In fact, you can even see random spanning trees as a special case of DPPs. So now let me tell you about the closure properties. So let's start with some simple one. Let's say mu is a strong Rayleigh. Let's start with this. I claim that mu condition on 1 complement. So by this I mean that conditioning on 1 not to be in my sample is a strong Rayleigh distribution. Can you prove this?
What does it mean?
So again, okay, so this means that so for every set S, this is equal to 0 if 1 is in S, and it is basically proportional to mu of S otherwise. You basically throw away every set that doesn't that do contain 1, and you renormalize on the sets that do not contain 1. Okay, so can you prove that this is strong Rayleigh?
So do you substitute like z1 equals 0 or something?
Exactly. So you just substitute by g of mu of 0 comma z2 so on. You just basically throw away everything that doesn't contain 1. You need to do a renormalization, but it doesn't change the real stability. So another thing, you mu condition on 1. Now you condition on element 1 to be in. You throw away everything that do not contain 1. How about this one? It's derivative, yeah. You just look at, it's basically z1 times partial z1 of g mu. Okay? So some simple exercises. Now we can do a more interesting operation called projection. So let's say, suppose T is a subset of N. I want to project on T. So what that means is that think about spanning trees, for example. You want to project your spanning tree onto a cut, let's say. You want to take the intersection of a random spanning tree with a cut. So in general, it means that, so let's say I'm going to use this notation, projection onto T. So it's like if I look at mu of projected onto T, the probability of a set S, this is equal to summation of mu of S prime, where S prime intersection T is equal to S. So I look at all of the sets whose intersection with T is exactly equal to S, and that's going to be the new probability of my set S. Okay. So I want to say projection preserves.
It's called push forward, right?
Huh?
It's called push forward.
It's called push forward.
That thing. So you have a map, right,
Yeah.
from one space to another, and your projection is called push forward of the map, right? So
I haven't heard of that terminology. Okay. Anyway, so can you see that this preserves real stability or strong Rayleigh?
So the variables in K to be 1?
Not to be in T to be 1. Yeah. So you set G mu of, for every, you set Zi to be 1 for all I not in T. Okay. Now let me say lemma. Simple consequence of these 3 facts. For every strong Rayleigh distribution mu, and any set, say, S subset of n, sorry, let's say T subset of n, S subset of n. If I look at it, the distribution of S intersection T for T sampled from mu. You sample, say, a random spanning tree, you look at the intersection of T with my set S. This is distributed as sum of independent Bernoullis. This is exactly the theorem Jan mentioned in his talk. Now I want to prove it. Okay, so this is not only true for all random spanning tree distribution, but it's also true for all strong Rayleigh distributions. Okay, so let me prove it. Any question? No question, let me prove it. So again, the proof is very quick. So first of all, I project my distribution mu onto the set S. Okay, so think of S, for example, as a cut. So you project your random spanning tree to a cut. So this is a strong Rayleigh. So let's say, let me write down the generating polynomial of this. Let's say the generating polynomial of G of mu projected to S is, let's say it has variables maybe Z1 up to Zk, okay? I mean, K is some number. It must be less than or equal to size of S. Okay, I mean, it will be, basically, yeah, it will be equal to size of S. Basically, I will have one variable for every element in the set S. So let's say this is the generating polynomial of the projected distribution. Then what I do is that I do symmetrization. I'm going to have the same variable for everything, for all of this. So this polynomial is real stable. Now this other polynomial of you project and say you put T for everything. This is also real stable. Remember, we're closed under, if I symmetrize. If I substitute for Z2, Z1, I still have real polynomial. So this is also real stable. But now this is a univariate polynomial. It's real stable, so it must be real rooted. So this is real rooted. Okay. Now I have a real rooted polynomial with non-negative coefficient. So I can use the theorem Jan mentioned yesterday that any real rooted polynomial with non-negative coefficient can be written as sum of independent Bernoulli random variables. So in particular, if I look at this polynomial, this is equal to summation of ak t to the k, where ak is the probability that that S intersection t, oh, I have k, L, let's say. This is the probability that S intersection t is equal to L. Okay, so I have this polynomial. The L's coefficient is the probability that I have L samples on my cut or on my projected distribution, and I'm saying that I can write this as sum of independent Bernoullis. Okay, so you get all sorts of nice properties out of this. You get that not only that you get concentration, you get that this distribution has satisfying Newton identities, it's log-concave, it's unimodal, and many other things.
So about 30 minutes in, you still owe us an explanation of the name Rayleigh.
Yeah. That would be the next thing. Okay, good. So, okay, so now I want to tell you about another properties of this strong Rayleigh distribution called negative correlation. But before that, I need to say a theorem of Brandon from book 6, I think. So it's a characterization of multi-affine real stable polynomials. So I prove the following. a polynomial P, let's say that a multi-affine polynomial. A multi-affine polynomial P is real stable if and only if for all I and j partial I of P x partial I of P at so j of x is bigger than or equal to partial I partial j of P at x. And this is true for all x. Okay. So that's a set of inequalities. So it's first of all, remember multi-affine means that your polynomial is square free. But this says that there are these basically n squared tests to check if a multi-affine polynomial is real stable. You just need to check if these polynomial equations are satisfied for every x in R to the n. Okay. So let me give an example to. So I want to say that this a special case of this implies so-called negative correlation property for real stable polynomials.
You want it for absolutely all x or just
for all x?
Positive ortant?
No, for all x. That's the interesting thing. So okay. So let P be G mu for a strong Rayleigh distribution mu, and let X be the all ones vector. So what is G mu of all ones? It's just summation of mu to mu of S, right? And that's equal to 1. What is partial I of G mu at 1? It's basically equal to all sets S such that I is in S, Z to the S over Zi, because when you differentiate, Zi will go away. So it's really this, you validate all 1. So this is equal to probability of I. And similarly, partial J of G mu at 1 is equal to partial to probability of J, and partial I, partial J of G mu at 1 is equal to probability of Ij. Okay. So what do I get? I do. Okay, let me.
The probability of I, you mean the probability that the set contains I.
Exactly. So the probability that if you sample a set from the distribution, it contains the element I. So this is also called marginal probability of the element I, and I will talk more about it later. So now plug this into that inequality. Okay, I can plug it in here. I get that probability of I times probability of j is bigger than or equal to probability of I comma j. Or to put it differently, probability of I is bigger than or equal to the probability of I condition on j. Meaning that if I condition on j to be in my sample, this can only send down the probability of I. Okay. So we already knew, for example, for random spanning tree distributions, they are negatively correlated from Kirchhoff's formula like 100 years ago. But this actually says that this thing holds for any real stable polynomial, for any strong Rayleigh distribution. Now. So now what I proved so far, or sorry, what I discussed so far, is when you plug in x equals 1. Now you can ask what happens if I plug in other values of x. You can actually plug in x to be non-negative, and that kind of gives you this for conditional distribution. So it says that not only your original distribution is negatively correlated, if you condition an element to be in or out, still it is negatively correlated. Okay? But, so that is called Rayleigh. So there are matroids called Rayleigh matroids, which satisfies this inequality only for non-negative x's. And the whole point of this sort of Borchardt-Brandon-Liggett result is that you can actually now define a generalization. They call it a strong Rayleigh, that they not only satisfy this for non-negative vectors, they satisfy this for every real vector. And now not only you get negative correlation, you get many other properties that you wouldn't have. Okay, so let me summarize. So for Rayleigh matroids, for Rayleigh distributions, we have that partial I of p at x, partial j of p at x is bigger than or equal to partial I, partial j of p at x times p of x for all x bigger than or equal to 0. And this is basically equivalent to negative correlation and some generalizations like conditional negative correlation. But now we have stronger property that is holds for every x in the real in R to the n, and that's why we get a lot of other properties.
Is there some interpretation like negative correlation for negative x?
That's a good question. That's like one of the things. Actually, it would be interesting to figure out a probabilistic statement of that you can. Yeah, that's actually I don't know.
Is that statement? Is there some way to rewrite it in terms of like a Hessian of log p or something?
Yes, exactly. Yeah. So this statement says that the off-diagonal entries of the Hessian of log p are negative. So let me also say that. So. So negative correlation means that if you look at the Hessian of log p, so this is a matrix. This is an n by n matrix. You can evaluate it. You can look at the ij entry and then evaluate it at the all ones vector.
So it's the same as the monotonicity statement I'm talking about.
So wait a second. So if the Hessian is exactly the ij entry of the Hessian is exactly this, that the left-hand side minus the right-hand side minus the left-hand side. It's the right-hand side minus the left-hand side. So this says that basically at every x, if you evaluate this at every x, the off-diagonal entries of the Hessian would be of the Hessian of the log would be non-negative, non-positive. Okay, so this is less than or equal to 0 for all x.
Oh no, this is not exactly Hessian. You need to divide by p squared.
Sorry, I need to divide by p squared. You're right. I need to divide by. Yeah. Okay.
So
this is.
in the homogeneous case, diagonal is also fine on the positive order.
You're right. I think it's better to say it for all ones. Let's say it for all ones. It's better. Yeah, you need to divide by. Yeah, sure.
And in the homogeneous case, diagonal is also fine on the positive order.
In the homogeneous case, you're going to be.
Because in the homogeneous case, you will have log-concavity.
Yes.
And
I mean, you have log-concavity no matter what. Like if it is real stable, you have log-concavity.
but not
the other way around.
Not everywhere on positive.
You're log-concave everywhere on positive order. If it is.
You don't even guarantee that you're positive everywhere.
Okay. You don't get, I thought you get. If it has non-negative coefficients, I think you get. Yeah, that's what I'm saying. I'm talking about distributions. Yes. If you have non-negative coefficients, you're log-concave everywhere on the positive order. Even if you're not homogeneous.
So, but if you look concave everywhere, then the diagonal is also fine.
Then what?
Then the diagonal is also fine.
If you're.
Because that is actually minus Hessian.
That's.
If you subtract from that it's like minus Hessian.
That is the. Yeah, that's what I'm saying. I'm saying the off-diagonal entries are negative. Yeah, or non-positive. Yeah, that's what I'm saying. Yeah. Yeah, it was just, yeah, actually, you're right. If it is non-negative, oh yeah, you're right. Okay, I was right in the beginning. Okay, so good. So if P is if it is distribution, if you have G of mu, if P is a distribution, the coefficients are non-negative, then this is true for all x. All of diagonal entries for I not equal to j is less than or equal to 0. Any other questions? So actually, to point out to a later talk, so Nima will talk about log-concave distribution and log-concave polynomials. And there, instead of this condition, you will have the condition that this matrix, the Hessian matrix of the log, is negative semi-definite. So it's a spectral property as opposed to a coordinate property for this matrix. Okay, so now I said that. Okay, let me say the next.
That last sentence,
Last
which ended with positive semi-definite.
Oh, I'm saying there's a different thing, that instead of asking this matrix to have non-negative, non-positive off-diagonal entries, you ask that this Hessian matrix to be negative semi-definite. And this is called, so Nima will talk about it, these are called log-concave polynomials and log-concave distribution, or strongly log-concave. We'll see more about it later in the week. Okay. So this is called, we call this spectral negative correlation. So let me say the next thing. So now I want to say, okay, so I said negative correlation. Now I want to say the next thing, which is the truncation and homogenization. So it's another operation such that these polynomials are closed under. So homogenization. So this is again a theorem due to Gaussian, Brandon, and Liggett. So let's say, okay, first let me define it. Definitions. So say, again, you have a polynomial P. The homogenization of P of H, is defined as this. It's a polynomial on, let's say P is on n variables, z1 up to zn. The homogenization of P is defined on one more variable. So we add one more variable to make it homogeneous. And this is defined as P of z1 over z of n plus 1 all the way to zn over z of n plus 1. And you multiply it by z of n plus 1 to the d max. By d max, I mean the maximum degree of all monomials of P. So this is max degree of all monomials. Okay, so for example, if P is equal to 1 plus z1 squared minus z1, z3, z4 plus 2, z5, z1, then this has degree 3. So I need to add a new variable, z6, and then my new polynomial P of H would be z6 to the cube plus z6 z1 squared minus z1 z4 plus 2 z5 z1 z6. Okay. Now I can say this theorem of Gaussian, Brandon, and Liggett. So they say that if P is real stable and non-negative coefficients, then P of H is real stable. Okay. So you need an extra condition. You need the polynomial to have non-negative coefficients. And this is a necessary condition. If you don't have that, this is not necessarily true. So for example, if you look at 1 minus x, this is a real stable polynomial, but when you homogenize it, you get y minus x, which is not real stable. But if all of the coefficients are non-negative, polynomial remains real stable. I'm not going to prove this. I just want to use it. Any questions? So I want to say another operation, another closure operation of these strong Rayleigh distributions. So it's called truncation. So again, let mu be or distribution. Okay, so let me be a distribution, and k to be between 0 and n. And the truncation of mu, called mu k, is mu conditioned on sets of size k. So it's mu conditioned on sets of size k. You basically throw away every set where its size is not equal to k, and then you renormalize. So that's called the truncation. And okay, now you can use this to prove that if mu is a strong Rayleigh, then for all k, mu k is a strong Rayleigh. How to prove this? You basically again need to use the closure properties of real estate polynomials. So if mu is strong Rayleigh, G mu is real stable. Now I can homogenize it. So G mu of H is real stable. Remember that because I have a distribution, the coefficients of G mu are non-negative, so I can apply this theorem. And the homogeneous polynomial is still real stable. Now I want to, now this is a polynomial in n plus 1 variables. I want to only keep the monomials which have degree k in the original n variables. So I want to throw away everything else. So what I do is that I take the n minus k partial of zn plus 1, of the new variable. And then evaluate zn plus 1 to be 0. This is similar to an exercise we did yesterday. Like you have a polynomial, you want to just keep the monomials that have degree n minus k in zn plus 1. In other words, the degree in the rest of the variable is, this should be d minus k. If the original polynomial has degree d max, the original polynomial has degree d max, I want to keep only the terms that have degree d max minus k in the new variable. In other words, in the original polynomial, the monomials which have degree k. So I take d max minus k partial derivative, evaluate it at 0. I only keep monomials that have degree k, and this is exactly give me the mu k distribution. So a simple consequence is that you can define, there was this question of what happens if you restrict or you condition your DPP to have size exactly k. This is called KDPP. So KDPPs are DPPs where you condition the size to be exactly equal to k. And you get that KDPPs are a strong Rayleigh. So, for example, they are negatively correlated. That's actually a non-trivial fact. Like I was reading some of these surveys on these determinantal point processes, and it seems that they expect these KDPP distributions to be positively correlated. Because when you condition the size to be k, it seems you are sort of enforcing like some positive correlation. Because it's like you're saying if this guy should be in, there should be some other correlation between the other elements, but to opposite of what their instinct, it's actually negatively correlated. Another example is if you have independent Bernoulli random variables and you condition k of them to be sampled. Again, it's a strong Rayleigh, even though it's not independent Bernoullis anymore.
I think if you fix the size, right, then the intuition goes the other way. So if someone in, then just less room for everybody else.
Yeah, but
by the way, this operation is the main thing which is responsible for van der Waals-like inequalities.
The truncation.
Induction step, that one.
Mm-hmm.
Derivative
Sure.
and put 0.
Yeah, I agree, yeah. Okay, good. So I have, I started the 11:20. Let me say one last thing, and then we go for the break. So this is a topic which seems very off from strong Rayleigh distributions, but actually it has had a lot of applications when you combine this technique with the techniques with this theory of strong Rayleigh distributions. So let me briefly talk about it. So before getting to this, I need to define I need to define two things. First, Newton polytope. So what is a Newton polytope? It's basically the convex hull of the indicator vectors of the support of a strong Rayleigh distribution. So it's the convex hull of all 1s's, where S is in the support of mu. That's called the Newton polytope. So one example is the spanning tree polytope. So you choose a random spanning tree distribution. You look at the indicator vector of all spanning trees, and that that would give you you look at the convex hull of them. That would give you a Newton polytope of that polynomial. Okay, so that's one definition. So one more definition, which is called symmetric exclusion. External fill. So let's say I have a vector lambda in n-dimensional vector which is non-negative. Okay. If P is a strong Rayleigh, P of z1 up to zn is strong Rayleigh, then P of lambda 1 z1 up to lambda n zn is a strong Rayleigh. If you scale zi by lambda I, as long as all lambda i's are non-negative, this remains strong Rayleigh. That's again simple to see from the closure properties of a strong Rayleigh distribution.
Sorry, do you mean real stable?
Sorry, I meant real stable. The analog for distributions is that if mu is a strong Rayleigh, then let's call this lambda star mu. Where this is the polynomial, the generating polynomial is just lambda 1 z1 up to lambda n zn. Then this polynomial is a strong Rayleigh as well. Okay. So strong Rayleigh distributions are closed under external fields. So is the real estate polynomials. So I want to say this theorem. So let P be a point in the Newton polytope of your strong Rayleigh distribution. So let P in the interior of Newton polytope of let's say G mu. Then, so interior means that it's not on the faces. There exists lambda, there exists the external field lambda, such that marginals of lambda star mu is equal to P. So what does that mean? That means that for all I, the probability of I in the distribution lambda star mu is equal to Pi. Okay. So why is that interesting? That's you start from some distribution. It has some marginal probabilities. But you may be interested in some other distribution with some other marginal probabilities. This says that as long as your target marginal probabilities is inside the Newton polytope, you can perturb the distribution by applying an external field to get to any point of your interest. And still you will have a strong Rayleigh distribution. Okay? And furthermore, you can compute lambda efficiently. Okay?
This is, because some people are familiar, it's a scaling.
Yes, I'll talk about it. Yeah. Yeah, you can actually see this in many ways. There are like a lot of papers who study variants of this in very, very different languages. So I guess you can see it, as Kovic says, as a scaling. You can see it as max entropy distributions. You can see it as so let me briefly say how you prove this, and then we can go for the break. So the proof, there are actually multiple ways to prove it. One way is to prove it by max entropy distribution, but there's a dual proof by scaling, which is, I think, quicker and maybe nicer. So you look at the following polynomial. You minimize log of g mu of z1 up to zn over z1 to the p1 all the way to zn to the pn. And this is the infimum is over all z's which are non-negative. I claim that the optimum, if you optimize this, you plug in lambda for the optimum z, that exactly gives you the right external field. Okay. So first, why can you solve this? So how to solve? Again, it's just the convex programming. So basically, you do a change of variables. You substitute e to the yi for zi. This is similar to a convex program I talked about yesterday for approximating the permanent, except you didn't have the pi's in the denominator. So you substitute here. Then basically you just have log of g mu of e to the y1 up to e to the yn minus summation of pi yi.
For this, you don't need Rayleigh, right? You need only positive coefficients.
Exactly. In order to solve this, you just need to g mu to have non-negative coefficients. As long as g mu have non-negative coefficients, you can do this optimization. This is a convex function. And this is, again, log sum exp. And it is convex as long as, this is actually convex. So log sum x is convex. Okay. So in fact, you can solve this optimization problem as long as you can evaluate your polynomial. So it turns out that for a strong Rayleigh, you can evaluate these polynomials. There are other examples like log-concave polynomials that you can also evaluate this, so you can solve analog of that, for example. Okay. Now, one last line, and then.
What do you mean for strong Rayleigh? You can evaluate.
For log-concave, huh?
What do you mean you said for strong Rayleigh you can evaluate it?
Yeah.
What do you mean by that? So
if you plug in for z1 up to zn, you want to see.
I can always plug in. What do you mean strong Rayleigh?
Well, I mean, this can have exponentially many terms, right? You want to evaluate it polynomially.
Okay, but how is the polynomial given to you then?
Let's say you know the coefficient of each monomial.
Okay.
You mean you have an oracle for the
Yes, you have an oracle. Yeah, that's what I mean. You have an oracle, so because it can have exponentially many coefficients.
No, but what it has to do with Rayleigh?
What's that?
But what it has to do with Rayleigh?
There is an algorithm that if it is a strong Rayleigh and you only know the coefficients as an oracle, then you can evaluate this. I'll talk about the algorithm briefly in the discussion section, but it's a Markov chain algorithm. It's a non-trivial statement. Okay, now how do you prove this? Basically, you just write down the optimality condition here. So you just differentiate this with respect to zi. You get that partial, I know that partial zi of this log of g mu over z1 to the p1 all the way to zn to the pn should be 0. Now you do the differentiation, so it's the same thing. It's basically partial zi of log of g mu must be equal to partial zi of pi times log of zi. So you do the differentiation. This is really partial zi of g mu over g mu must be equal to pi over zi. Just doing the derivative of the log, and so this is equivalent to this, and this is equivalent to that, and this is equivalent to that zi times partial zi of g mu over g mu is equal to pi. And what is this? The numerator is exactly the generating polynomial of all subsets that contain the element I. This is the generating polynomial of everything. So this is exactly the marginal probability of I. It has to be equal to pi.
This is not the proof, because you need to prove first that infimum is attained. This is the main thing.
Okay. But yeah, this is okay. This is the main, I guess.
Yeah.
Sure.
Okay. Because again, many people, this is the main. It's not a big deal, but this is in all those scaling results. The main thing is to prove that it attained.
I agree. There's a technical part. Yeah, there are technical parts. You need to say the infimum is attained and so on. But yeah, the upshot is that this is actually what you want. That's why you want to do it this way, because it's exactly certified that that the marginals are equal to p. Okay. So, any questions?
So by the way, so the infimum is not necessarily attained, right?
But if it's inside of that, of course.
That's why you need to be inside the interior of the polytope.
In the interior. Okay.
Yeah, if you're outside.
Yeah, I understand.
Okay, so there are some technical things. If you're outside of the polytope, then it's not attained at all. If you're on the polytope, then some lambdas can become infinity. But if you're in the polytope, it's always attained. And if you're not in the interior, you're on the boundary, you can find a sequence of these polynomials that converge to your thing. So you can. So yeah. Okay. Okay, so if no question, maybe let's resume at 12:30 for like a 10 minutes open problem session.